Welcome to our session on statistical computing. Today we are going to dive into one of the most fundamental and important concepts in C and C++ programming, how the computer handles text. We will explore character arrays, strings, and the hidden mechanics that keep our programs running smoothly. Understanding this will give you a massive advantage in writing secure code. Let us start by understanding what a string actually is and why it matters so much. Imagine a string as a passenger train traveling down a track where each car holds exactly one letter. But how does the station master know where the train ends? In C and C++, a string is simply a one-dimensional array of characters, but it must always end with a special invisible marker called the null character. This acts as a hard stop sign. Without it, the computer would keep reading memory indefinitely, printing random garbage values until the program eventually crashes. Now that we know what a string is, let us look at how we allocate memory for it, conceptually. When you declare a character array, you must tell the computer exactly how many slots to reserve. The formula is simple. The total size equals the number of visible characters plus 1. That plus 1 is absolutely critical. It represents the mandatory extra slot for the invisible null terminator. If your text increases in length, the required memory size increases by the exact same amount, always staying one step ahead. If you forget this, your program will suffer severe memory errors. Before we move on, let us see this with a concrete visual example. Here we see the memory representation of the word hello. Notice that while the word only has 5 visible letters, the array requires 6 slots, indexed from 0 to 5. The letters fill the first 5 slots, and the 6th slot at index 5 holds the null terminator. This hidden stop sign is what transforms a normal collection of characters into a valid string that the computer can safely process. Having seen how strings are stored, we must now distinguish between the two main ways to create them. The first is a character array, which is like writing on a classroom whiteboard. You own the memory, so you can easily erase and change letters. The second way is a string literal, created using a character pointer. This is like text carved deeply into stone. It is stored in a special read-only section of memory. If you try to change even a single letter of a string literal while the program is running, it will instantly crash. Understanding memory ownership brings us to a critical security issue regarding input. Standard input functions stop reading at a blank space, so programmers used to rely on a function called gets to read full sentences. However, this function was incredibly dangerous and has been banned from modern C. Why? Because it never checks how much space you actually reserved. If you reserve 10 slots, but the user types 100 characters, the data spills over, causing a catastrophic buffer overflow that destroys neighboring memory and creates severe security vulnerabilities. Because strings are technically just arrays, we cannot use normal mathematical operators like the plus or equal signs to manipulate them. Instead, C provides a special toolkit called the Standard String Library. Think of these as specialized power tools for text. The 4 most essential functions allow us to find the length of a string, copy text from one variable to another, compare two strings alphabetically, and concatenate or glue one string onto the end of another. This brings us to our first standard library tool. Let us look at how the length function works mathematically and conceptually. The formula is L equals strlen of our text. In this case, the word data. Here, L represents the integer count of visible characters. The strlen function is specifically designed to scan the array from left to right, counting each letter until it hits the hidden null terminator. It intentionally ignores that final marker because humans only care about the visible letters. If the string gets longer, this function simply counts further down the array before stopping. Before we move on, let us see this with a concrete example. We want to find the length of the word data. The computer scans the array starting at index 0. It counts the 4 visible letters one by one and stops the exact moment it sees the null terminator. The final calculated length is exactly 4. However, remember our earlier rule? The physical memory size required to store this string safely is 5 bytes because the computer absolutely needs that extra byte to prevent crashing. Now that we understand length, let us look at how we combine or concatenate strings. The formula to predict the final visible length is sFinal equals sdest plus ssrc. sFinal is the total number of visible characters after gluing the two words together. sdest is the length of the original word in the destination array, and ssrc is the length of the new word we are bringing in. We must calculate this beforehand to ensure our destination array has enough empty space to hold both words without overwriting other important data in memory. Let us apply this formula to a real scenario to see how it works in practice. We have a destination array containing the word stat with a trailing space and a source array containing the word computing. We want to append the source text to the destination text. First, we determine our known lengths. The first word has 5 characters, including that blank space at the end. The second word has exactly 9 characters. We are setting up our equation carefully to ensure we do not overwrite important data. Continuing with our calculation, we substitute these values into our equation. We simply add 5 and 9. Behind the scenes, the concatenation function automatically removes the original null terminator from the first word, pastes the second word in its place, and adds a brand new null terminator at the very end. The final visible string length is exactly 14 characters. To do this safely, the destination array must have been originally created with a size of at least 15 bytes to prevent a catastrophic buffer overflow. We have covered a lot of ground today. Remember the 3 most important ideas? First, strings in C and C++ are simply one-dimensional arrays that must always end with a hidden null terminator. Second, always allocate enough memory for that extra terminator to keep your program stable. And third, rely on the standard string library functions to manipulate text safely, avoiding outdated functions that risk overflowing your computer's memory. You now have a solid foundation for handling text in statistical computing. Great job!